Hello and welcome. For the next few classes, we will discuss states of matter, which is Unit 5 of NCERT Class 11 Chemistry. In this unit, we will discuss mainly three things. One is intramolecular forces, the second is gases, in which we discuss ideal and real, and liquids. Solids is dealt with, which is also a state of matter, is dealt with in a different chapter, different unit, whatever you want to call it. So, these are the three things that we will discuss: intermolecular forces, gases and liquids. We start off by looking at some things around us. So, if you look at things around us, what do we see? The first thing that we see is that we live in a blanket of the atmosphere. The atmosphere is composed of gases, that is oxygen, nitrogen, carbon dioxide, and if you happen to live in Delhi like I do, then lots of other things which we will not concern ourselves with. So, the atmosphere is the state of matter that we see, that is the atmosphere is a gas. Oxygen obviously is of great importance to us and our lives. The next most important thing in our lives is water. So, if you look at around you, or you walked into the kitchen, then you find water elsewhere too. Water is one. The other thing that you will find in the kitchen is the oil, and if you happen to have an automobile, then you will probably be interested in gasoline. These are all states of matter. The state of matter of these things is a liquid, but a predominant number of substances that we encounter in our daily lives, for example sugar, which is a cause of a lot of our problems in our health, salt, and kitchen vessels, for example iron vessels, etc., form are solids. So, these are what we call states of matter. These are typically the three states of matter that we divide whatever we see around us into. But this division of what we see into three states is in some sense a convenience thing, and you can't, for example, you will have trouble if you have to give a very strict definition of what constitutes a solid, liquid or gas. So, because the reason for this is that there are many exceptions to this definition, this characterization into solids, liquids or gas. For example, if you look at the window in many houses, this is made of glass. In appearance, glass appears to be a solid, of a solid, but in reality it is actually a supercooled liquid. What a supercooled liquid is not something that we will worry about right now, but the reality is that glass, although it looks to us like a solid, is really not a solid. So, there is this problem of definition or characterization into solid, liquids and gas based on what we see. So, what we need to do then is this characterization into solid, liquids and gas is based on some principal characteristics. The principal characteristics are compressibility. What is compressibility? If I took a substance and I applied pressure on it, a static pressure, and how does the volume change? So, this is one characteristic which allows us to differentiate between solid, liquid and gas. Compressibility, that is the volume change that occurs when we apply pressure to a system, a state of matter in this particular case. The other thing that we look at, the property on which this characterization goes, is rigidity. This is similar to compressibility, except that what happens here is that at constant volume, so at constant volume, if you apply some kind of pressure which changes the shape of the body, then this is called rigidity. So, the ease, the convenience, or how easy or difficult it is for us to change the shape of the body keeping the volume constant is what constitutes rigidity. The other thing that we look at is viscosity. Viscosity is the measure of resistance that a system has to change of shape taking place at finite speeds. And I think although one might not have an appreciation of this exact definition of rigidity, compressibility and viscosity, one has in our heads a typical idea of what it means. So, it is on this basis that one characterizes a state of matter as being solid, liquid or gas. So, let us first look at some of the characteristic properties of these three states of matter. So, if I take a solid, and the advantage of having the characterization of substances as solids, liquids or gases is that you can understand these things in terms of a kinetic molecular theory, and that is the reason why there is this characterization in some sense of states of matter in this form. So, if I take a solid, the solid is rigid, which means that if you apply a pressure on this does not change its shape very quickly. You take anything like this, you take a pen for example, if it is very difficult for me to change the shape of this unless I apply a lot of pressure. The second thing is that it has a fixed shape and it is not compressible. Whereas, for a liquid, it is not compressible in much the same way that a solid is not. So, if I took a liquid in a container and I applied pressure on it, you cannot change the volume very much, or you have to increase the pressure so much, so before it becomes compressible. It does not have a fixed shape. So, it takes the shape of the container, unlike the case of a solid. So, in that sense it is not rigid, and the other important thing is that it has, like a solid, it has a surface. So, if you put a liquid into a container, it has a surface. The reason I point this out is if you consider a gas on the other hand, this has no surface, it is extremely compressible. That is, if I take a gas and I apply a pressure onto it, the volume will shrink very easily, and we see this in everyday lives, and it takes the shape of the container. So, you can confine a gas into a container of any shape, but unlike a liquid, it has no surface. This difference between a liquid and a gas having a surface or not a surface, that is an interface, is something which is of great importance, because at the critical point whether it is a liquid or a gas is determined by whether there is a surface which differentiates the liquid from the gas. Okay, so what we said is that we can understand this solids, liquids and gases in terms of a kinetic molecular theory. So, what is this kinetic molecular theory? For that, let us try and draw a picture of what a solid would look like. So, I am drawing a 2-dimensional surface. It can be, you can make this into 3 dimensions, and we are taking molecules to be structureless. Molecules are structureless circles, call it. So, if you do it in 3 dimensions, it would be spheres. So, here I am just drawing it as structureless circles. So, in a solid, what happens is all the molecules are identical and they are packed together closely. So, I have something which looks like that. So, the things to notice is the molecules are in fixed positions. This empty space that we have here is very small, and this together in some sense characterizes how a solid behaves. So, if you apply pressure on the solid from here, because the molecules are on top of each other, you cannot compress it. Also, because the empty space is small, you cannot compress it. So, as a result of the spheres touching each other, you do not have very much empty space. So, you apply pressure, this has nowhere to go. Okay? But you have to notice is that what you have to notice is that each of these things, and I have taken a crystalline solid for convenience. So, these positions are fixed. So, this is the average position of the molecule. About this fixed position, these molecules vibrate. Now, if you raise the temperature, then the extent of vibration of these molecules will increase. So, they will be at the same position where they were at lower temperature, but the molecule vibrates more. So, about their fixed positions they vibrate more. This is the kinetic molecular picture of a solid. Now, on the other hand, if you now consider a liquid, it looks much the same. I draw the same surface, I have same size molecules, except now these positions of these molecules are quite random. So, they are not at fixed positions, they are at random positions. And they move about. This is something that we know from other experiments. So, these molecules in this picture are moving around at random. So, they under collisions with each other. So, this is how we understand the kinetic molecular theory, the molecular picture of a liquid. The empty space, although I have drawn it as it is very big, is small. It is higher than that we have in a solid, but it is still relatively small. The empty space is maybe in a liquid is about 3% larger than what you would have in a solid. And when these things move, if you have to apply, it is not easy for the molecules move past each other. So, if you have to get something to move, then you have to wriggle past one another, as a result of which the viscosity is quite high. It is not high compared to a solid, but relative to a gas, because these molecules have to slide past each other and wriggle past each other to for it to move like this, viscosity is slightly high or little bit higher than what you would see in gases. Okay. But because the empty space is small and the molecules are more or less packed close together, it is not compressible. Okay. So, that is the picture in the kinetic molecular model of a liquid. The gas on the other hand, if you thought about it, looks like this. They are completely, well, although in the picture it does not look random, the molecules are in random, there is lot of empty space. And because there is lot of empty space, when you apply pressure, the gas compresses easily. So, what we are now trying to figure out, so this is the kinetic molecular model of a gas, and now what we need to figure out is why does a particular state of matter adopt the form that it is the state it is in, or why do different compounds exist in different states of matter. So, if you looked at it, sugar is a solid at room temperature and pressure, whereas water is a liquid and oxygen is a gas. Is it possible that we can understand why something is a solid, another is a liquid and a third is gas using this kinetic molecular model? For this, one of the best ways to do that, one of the best ways to do it is to take a particular substance, let us say water, and conduct some transformation to it. So, what we will do is we will take ice, which is solid form of water, that is water solid, and we will do an experiment with it. We will take it in some container, we will take ice cubes and we provide heat to it, and we look at as a function of time or heat provided. So, if you are providing a fixed amount of heat for a particular amount of time, I can say either heat provided or time, whichever it is, and temperature. Let us think of what would happen. So, we start with ice at a temperature below its freezing point under normal pressure. So, let us imagine that we started at 20 degrees below 0 and we provide heat to it. You can put it into a kitchen flame or a Bunsen burner or something like that, and the temperature starts to rise. The temperature starts to rise up to a point where ice solid or water solid undergoes a change to water liquid. So, the temperature continues to rise as heat is provided when up to the point where solid is purely in existence, and when solid changes to liquid, then the temperature becomes steady, and this is the latent heat that we know of. At this point, you need to provide more heat to convert all the solid into liquid. Until that happens, the temperature is constant. So, this is the latent heat. Now, once that happens, after all the ice has melted into liquid water, you continue to provide more heat and the temperature rises after that, and it rises up to the point where all the liquid gets at one point will start converting into steam. When liquid gets converted into steam, which happens at 0 Celsius under normal conditions, you will then again have a latent heat. The amount of heat that you have to provide in the case of water in this case is much higher than what you need to do. So, this horizontal portion is going to be longer, and then after that, once all the liquid has been converted into steam, the temperature will again rise. So, this is what you would see. This is at 100, that is a mistake. So, this is at 0 degrees. Yes, that is correct, of course. Yes. So yes, this is, there was a mistake that was pointed out. I had written that initially it was 0 degrees Celsius. Its conversion from liquid water to steam happens at 100 degrees Celsius. Thank you. So this conversion happens at 100 degrees Celsius at the normal temperature and pressure at sea level, etc. Now, if you did the same experiment with some other substance, so you took for example salt or sugar or something like that, you could do the same experiment, provide more heat, it will melt, the temperatures will be different, the curve will look the same qualitatively. There will be one point where this breaks, it becomes steady, another point where it becomes steady, and so on. So, what we are saying is, for different substances, whether you take water or you take something else, you take alcohol, you take oil, all of them will do similar things, except that this point would be different and this point would be different, and obviously this lengths will also be different. But the problem with having this characterization into solid, liquid and gas is that not all substances will do this kind of behavior. There are instances, and that is where this problem of classification of solid, liquids and gas is a problem, because here in water or in alcohol or in something else, these breaks are very clear, but you also find things which look like solids which do not have this clear cut breaks. So, that is one of the reasons why you have this problem with classification, right. So, what happens, we have already said in the kinetic molecular theory, we said that if I started with here, I have this like this, and the model suggests that as I raise the temperature, these things start to vibrate about their fixed positions. So, and even if I have a liquid, then their motion becomes more and more violent as the temperature rises. So, somehow there is something which, there are two things that are playing a part. One is the thing which makes the solid go into this rigid form with the molecules stacked on top of each other or close to each other, which is counteracted by the temperature. So, larger the temperature, these things start to vibrate. So, we have two counteracting things. One is a force of attraction between molecules, counteracted by the temperature. So, that is what we need to understand. So, the reason for understanding this force of attraction. So, we have two things. One is the force of attraction, between molecules, that keeps the solid or liquid together, and the temperature tries to throw them apart. So, qualitatively you can say the temperature or thermal energy, as it is sometimes called, is roughly estimated per mole as RT, where R is the universal gas constant and T you could do it in Kelvin. So, if we have 8.314 joule per Kelvin per mole times 300 Kelvin, that works out to be about 2.5 kilojoules per mole at 300 Kelvin. That is a rough estimate. That gives you what the thermal energy is, and the force of attraction is what keeps the molecules together. So, if the temperature is higher than what keeps molecules together, then you will convert from solid to liquid to gas, and the extent of the temperature will then determine whether it is a gas or a liquid. So, what we need to understand is what is this force of attraction that holds molecules together. So, this is the intermolecular forces of attraction. Can we get a rough estimate of what is the size of this intermolecular force of attraction? How do we do this? Let us take a particular example. Let us imagine that I have Cl2 gas and I break this. If I break this, it will give me 2Cl gas, and the heat that is required to break the Cl2 molecules into 2Cl atoms gives you the bond energy or bond enthalpy if you are looking at it in terms of thermodynamics. And this bond enthalpy for Cl2 happens to be 242.4 kilojoules per mole. So, this is the typical covalent bond energy. And if somebody asks you this, approximately 100 to 400 kilojoules per mole is a typical bond energy. What we are now have to compare is what is the energy for us to do this. What we are saying is the intermolecular forces of attraction, which keeps chlorine as a liquid, will not exist, or it will be lesser in chlorine gas. So, the amount of energy that I need to provide for liquid chlorine to go to chlorine gas gives you an estimate of the intermolecular forces of attraction that exist in chlorine liquid, and this happens to be 20.4 kilojoules per mole. So, from this example, which is just illustrative, it tells you that intermolecular forces of attraction, and this is a positive quantity, which means that you have to provide energy to break some bonds. So, the intermolecular forces are smaller than typical covalent energies, covalent bond energies. So, what are the typical sort of intermolecular forces of attraction or repulsion? It could be repulsion too, that exists between molecules, and what are their sizes? So, at the end of this section, you should be able to list the intermolecular, the types of intermolecular forces to identify in a molecule or series of molecules the kind of intermolecular force that is predominant, and 3, given a list of molecules, to arrange them in their correct order of some physical property. Which is dependent upon the intermolecular forces. So, these are the 3 things at the very least that you should be able to do at the end of this unit on intermolecular forces. So, let us now first get a handle of kinds of forces that exist between molecules. So, this is the list, and I will give you the strengths, approximate strengths right away, and then we will go into what these things are in a little bit more detail. Now, these are very, very rough estimates. So, the thing that we already know of is ion-ion interaction, and as for example, you will find in sodium chloride solid. This is a relatively large interaction, and it has typical values of 600 to 1000 kilojoules per mole. Now, when I write numbers like this, if you go and look at a book, you will find different numbers. So, do not get too worried about if the numbers do not exactly match what we are saying. We only need a rough estimate of this. So, this is the biggest interaction that one will see between two molecules. The next one that we have is hydrogen bond. If you are unable to figure out what a hydrogen bond is, that we will do by the end of when we finish this thing on intermolecular forces. This hydrogen bond, the typical energies are 10 to about 40 kilojoules per mole. Once we have this, the next one is ion dipole. So, an ion here interacting with a dipole, and this ion dipole is of the order of 15 kilojoules per mole. So, we had ion, an ion interacting with a dipole, and you can just apply to your electrostatics a little bit. So, the next thing that we are likely to see is dipole dipole, and from now on it just follows exactly the way you would expect it to. Ion, dipole, 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 and this is of the order of 2 kilojoules per mole. Now, one thing that you have to note is that the hydrogen bond is just an extreme case of a dipole dipole interaction, but we classify it a little bit differently because its strength is different and it behaves a little bit differently. After this, we have dipole induced dipole. So, if I have a dipole and it comes to another near a molecule, it induces a dipole, and this is of the order of less than 2 kilojoules per mole. And last, which is not very difficult to understand. So, I have gone ion, dipole, induced dipole, and the next guess is induced dipole, induced dipole. And this is also very small, but very important. And this one, people might call it London dispersion. And often all three of these or all of them, maybe the ion-ion and the ion dipole excluded, would be called van der Waals interaction by some people, right. So, these are sometimes called van der Waals forces, because van der Waals, when he designed this equation of state, it dealt with intermolecular interaction. So, this gives you a rough picture. Before we get into what it means, it gives you a rough picture of the sizes of interactions that exist within molecules in different states of matter. Okay. So, if you want an exercise, here is something that you could do. Given that we have this situation, let us see if you can classify this. So, here are 4 substances: argon, chlorine, methane and acetic acid, and we would like to arrange this in increasing order of intermolecular interactions. So, what do we need to do? This is the kind of thing that we expect that you would be able to do at the end of this unit. If you can do this now, that is even fantastic. What do you need to do? We need to identify in a series of molecules, in a series like this, we have to identify which of them behaves like an ion, which of them has a dipole, or whether it has a dipole or it does not have a dipole. Now, whether a dipole can be created, that is, it can be induced, which will depend upon the polarizability, whether it has a group which can hydrogen bond. These are the kinds of things that one would like to be able to do. So, this is a typical kind of question that we hope you would be able to answer after you have gone through this unit. So, with this thing, let us move on to looking at the kinds of interactions. So, if I take sodium chloride in a solid, we already know its structure. So, we know the structure to be Na plus and Cl minus arranged in a particular crystalline lattice in cubic form. The electronegativity of chlorine, and the reason it exists in this is that electronegativity of chlorine is 3.0 and the electronegativity of sodium is 0.9, which means that chlorine has a tendency to pick up an electron because this electronegativity value is high. So, in the solid state we expect that sodium chloride would exist as Na plus and Cl minus. And when we have this situation, we know from electrostatics there is a force or an energy of interaction which is given by Q1 Q2 over Kr, where r is the distance between the two species, Q1 Q2. So, in physics you will typically have whole charges. In this particular case you may not have. So, if you took sodium chloride, you have some amount of covalent character and some amount of ionic character. So, you might not have complete positive and negative charges. So, that is the difference between what you would see in electrostatics that you would see in physics and the case that we have here. So, here the intermolecular potential energy is a function of the charges on the two species and the distance between them. So, if I took this and sodium chloride, as a result of this interaction you have what is called the lattice energy. The lattice energy is the energy that sodium chloride has as a result of it being in a particular lattice, and that arises primarily due to this electrostatic interaction. So, if you took sodium chloride and put it into water, you have to get rid of this lattice energy, or you have to gain some energy from somewhere else to compensate for this. That is what it means. So, if a substance does not dissolve, if an ionic substance, so you take for example lead sulphate. Lead sulphate also you would expect would exist as Pb2 plus or SO4 2 minus, but lead sulphate when you put it in water does not dissolve, whereas sodium chloride when you put it in water dissolves. The reason for this difference is that sodium chloride gains more energy when it goes into water, which compensates for this lattice energy, whereas lead sulphate there is not enough compensation that you get from when it goes into water. So, it stays as solid. So, the lattice energy is critically dependent upon the electrostatic interaction between these two ionic species. So, you can imagine if I go from NaCl to MgCl2, you expect that the lattice energy would be even higher. So, the first thing that, so if you took a series of compounds, the lattice energy would be a function of the size of this ion and the charge of the ion, right. So, what is a physical property which will reflect this? So, the one thing that will reflect this is melting point. So, what we are now saying is that if I took a series of compounds and looked at their melting point, does it show a trend? And here is an example. You look at lithium fluoride, it has a melting point of 848.2. So, this is the melting point represented in Celsius. Lithium fluoride has a melting point of 848.2. Lithium chloride, what do you expect? The lithium chloride, the melting point would be greater or less than lithium fluoride. If you have an understanding of the electrostatic interaction and the electronegativity of fluoride and chloride and their sizes, then you would be able to predict it. So, as you go down the periodic table, we know that the size of the ion would increase, which means that the same negative charge is distributed over a larger space. So, you expect that this interaction between lithium and chlorine would be smaller than the interaction between lithium and fluorine. As a result, we expect that the melting point of lithium chloride would be smaller, and it turns out to be 610. Now, you can go down this group, this period, and you will see that lithium bromide has a melting point of 550 and lithium iodide has a melting point of 469. So, here is a clear evidence that ion-ion interaction decreasing, the cation in all these cases is the same, but the anion is going down the halogen period, and the ion-ion interaction decreases because the size of this ion increases. And so, this is a clear reflection that the ion-ion interaction decreases as we go down this. Now, here is another example that you can try and do. Match the lattice enthalpies that we have given in the right column with the compounds in the left hand column. You should be able to do this now. So, here is the compounds on the left, and here is the lattice energy that we know has been measured, given in kilojoules per mole. LiCl, the compounds are this. So, here are 4 compounds, and here are 4 lattice energies that we have measured, and you should be able to match the compounds here with the lattice energies that were given here. And if you are able to do this, then presumably you have an understanding of how ion-ion interactions vary as the size and the charge of the ions vary, which is what we will need to do. Now, the potential energy that we have of this electrostatic interaction. So, V as a function of distance goes as 1 over r. So, I am taking it that I have a positive ion and a negative ion, and this distance is r. So, this is an attractive interaction. If I have two positive ions, then obviously I have a repulsive interaction like this. So, this is for two positive similarly charged, two like charges, and this is for two unlike charges. So, there is this attractive potential. What we are saying is that when we have intermolecular attractions and we look at, for a typical case, when you take not necessarily ion-ion, for two molecules, now we are looking at two molecules as a function of distance, not charged. What we are saying is that as you bring these closer together, there is an attractive force. So, I am now plotting V of this interaction as a function of the distance between these two objects, molecules. And I am varying this, I am taking this as two spheres to make life easy, because if I have two spheres, then no matter which orientation it is, it does not make a difference. The only thing that matters is the distance between the two. If I had two objects, so if I had two real molecules who have different shapes, then when I bring the molecule here or I bring the molecule here, their energies would be different. I do not want to deal with that. I am just dealing with two structureless molecules and I am bringing them together. So, no matter which direction it is, it is only the distance between the two that matters. And I am looking at the energy of this interaction as a function of the distance. So, if I bring them together, initially they are off at a distance and presumably these two molecules do not interact. So, if I have two molecules that are really far apart in space, there is no interaction, and we will take it that this is 0. And in all of these, what we are saying is attractive interaction means that if I have two molecules, the molecules would like to come together. So, this is negative. So, if I have two molecules like this, if I fix this to be the origin and I have the molecule here, the repulsive force means it is going in the plus x direction. There is a force of attraction means that it likes to come together. And rather than deal with force, I am dealing with energy, because I know how to relate the force to the energy. So, the potential energy is related to the force, right. So, if I know the potential energy, I can calculate by the force by just taking minus dV dr. And the advantage of using the potential energy is that it is not a vectorial quantity. Force is a vectorial quantity, energy is not a vectorial, it is a scalar. So, I prefer to deal with this. I am saying now I take two molecules far apart, and the analogy that we can think of is that you have in your system a solid, you have all these molecules which are similar or identical in all respects. So, think of a lot of identical twins, and they are all sitting at large distances apart. There is no interaction between the two, and that point we take 0 of energy. When the distance between these two molecules is far apart, they have correspond to 0, and we are saying as the molecules come together, the energy starts to drop. So, there is this attractive force, and it comes together. So, the molecules are coming together, we are bringing these things together and the thing drops. Now, what happens is at some point the electron density of this molecule will start to overlap with the electron density of this molecule, and then things will get a little bit difficult. Now, the molecules do not like each other because their electron densities are start to coming to on top of each other. So, this at this point this thing will start to rise. So, up to a point there is this attractive force, but once the electron density of one molecule starts to overlap with the electron density of the other molecule, then they start to object, and then there is this repulsive force. So, this is where the molecules tend to go apart. So, we are saying that the repulsive force is short range, that it operates at short distances, whereas the attractive force is reasonably long range, right. So, this distance here corresponds to approximately the distance that you have between two molecules of this system in the solid state. And this here gives you approximately, for two molecules, it gives me what is the energy of interaction. Now, in a solid, if you have things like this, there are lots of pairs of molecules. So, in principle I have to do this for every pair interaction, but when you bring three molecules together, there is also an interaction between three molecules and then four molecules, etc., etc. But electrostatics, we can just consider two molecules. So, for every pairwise addition you can do. We are ignoring all these many particle interactions. So, this is for just two molecules, not a mole of molecules. So, for two particles, this is what it is. And what we are saying is, if the thermal energy is greater than this, then the molecules will tend to go apart and the solid will break down, and it will give you, it will go into a liquid state, and if the thermal energy becomes even higher, then this will become a gas. So, we have to counteract this attraction before you can go into the gas state. So, now this is an understanding that we need to have as to what is it that we are doing. So, the first interaction that we have looked at is ion dipole. The next thing that we could look at, ion dipole. We already discussed this. So, if I take sodium chloride and I put it in water, so if you wrote this as a chemical equation, this will be NaCl solid. When I put it in water, gives you NaCl aqueous. And what we said earlier is that to go from here to here, the thing that keeps this together is the lattice energy. And when NaCl goes into water, what you are going to get is Na plus and Cl minus. So, if I have this, I will have Na plus like this, and I will have molecules of water sitting around like this. This is Na plus. So, this is an ion, right, and similarly around Cl minus I will have the same thing. So, both around sodium as well as chloride, you have this surrounded by a ring of water, and then you will have more and more layers of water. I have just drawn the nearest neighbor, the neighboring water molecules, right. Now, we know that if you looked at water, there is this, there is also an electronegativity difference between oxygen and hydrogen. and this electronegativity difference is exactly like what you would have in the electronegativity difference here, but except that the difference is not as large. If the difference is not as large, you will create what is called a dipole here. There is a small negative charge here and a small positive charge here, leads to a dipole which looks like that, positive charge there. So, if I take one single bond, if the electron density were equally divided between these two, I will have some electron density which looks like this. But because the electronegativity of oxygen is greater than that of hydrogen, I will have more electron density around the oxygen and less around the hydrogen. So, I will get delta minus delta plus, and when I have this, it is a dipole, and I have an ion here, I have a dipole here on this water molecule. So, you expect that there will be an interaction between ion and this dipole. This is an example of an ion dipole interaction, and we will look at how this behaves as a function of the distance, as a function of the charge on the species and the size of the dipole in the next class. We can stop here now, and in the next class we will go over the other intermolecular forces of interaction before we move on to gases. Thank you.